a phase shift oscillator is given, whereas GV2 is voltage gain of ideal amplifier and it is a negative real number. If we normalize the time constant Rc equal to tau equal to 1 second, what is the frequency of oscillation in radians per second? To approach this problem, let's first see what are the conditions for this circuit to oscillate. The condition is that if the input signal, so if you cut here, for example, the loop, this becomes an input signal and this becomes an output signal. We will have stable oscillations when in this system we have an input signal and at the output we have exactly the same input signal, both in magnitude and in phase. Which means that, okay, so the gain, of course, the open loop gain from this point to this point, the magnitude transfer must be 1, and the phase rotation must be n times 360 degrees. So, given that GV is a negative real number, so this condition, this means inversion. So every stage GV2 inverts the signal. So this means phase rotation of 180 degrees, exactly at every GV stage. So then what we know for the RC stage is that it rotates from 0 to minus 90 degrees. And we have 3 identical stages, which means that, so 3 identical stages, GV plus RC stage, from here to here, I mean, identical stages. So these are 3 the same, exactly the same. This means that the total phase rotation of 360 degrees will be rotated, will be divided by 3, and each of the identical stage, RGV and RC, should rotate to 120 degrees. So we have 180 degrees, and then the RC stage rotates the phase from 0 to minus 90 degrees. So we will take minus 60 degrees, and for this frequency we will have a phase shift of one stage GV to RC equal exactly to 120 degrees, which is derived as 180 degrees due to the inversion of GV2 stage, and then the RC stage must rotate exactly minus 60 degrees. So the frequency for which an RC stage rotates the phase exactly minus 60 degrees is the frequency of oscillations, because only for this frequency the Barkhausen criteria for oscillation are satisfied. Only for this frequency in the total open loop we can have a phase rotation of 0, phase rotation of n360. More accurately set 360 degrees, which is the criteria for oscillation. So now the question is, what is the frequency for which an RC stage rotates the phase minus 60 degrees? So let's see the characteristic of an RC stage. So it is, you can derive it as 1 plus S tau, where tau is RC, and we normalize it to be easier to 1. So now the equation, the transfer characteristic of the RC stage in S domain becomes very simple, 1 plus S. Now the question is, what is the frequency for which the phase of an RC stage is minus 60 degrees? So what is the frequency? Now let's see in S domain, in S plane, so this will be sigma and this will be j omega. We have one pole, one negative pole at minus 1. So this is the pole of an RC stage. So these are the frequencies. And then we will evaluate for different frequencies. For example, if we evaluate for the corner frequency, here we will have exactly 45 degrees phase rotation, minus 45 degrees, and we need 60 degrees. So if we have here 60 degrees or minus 60, because this is a poem, we will take it in the total transfer with a negative sign. Then the question is, what is this frequency? And this will be omega 0. Now let's consider then, because you can answer this question without calculating, just reasoning. What we see is that the frequency cannot be 1 or less than 1, because we know that exactly at the pole frequency the phase rotation of an RC stage is minus 45 degrees. So this is the pole frequency. This is the pole frequency, and now we'll have minus 45 degrees. For frequency lower than the pole frequency, the phase rotation will be less than minus 45 degrees, which means that I can eliminate this answer. This is also less than 1, and I can eliminate this answer, and I can eliminate this answer. Now I'm left with 4 options. So this is very large. These are very close actually. But let's look at the picture. So the frequency of oscillation will be actually this thing here. So this height. And this is approximately, so this is exactly 1. This is 1, because this is the frequency, the corner frequency, which is normalized 1 to, you know, if the time constant is normalized, this is 1 over tau, so 1 radian per second. Now, what is this? When here I know that it's 45, so 60 degrees is still 15 extra, and the closest will be this answer, and this is the correct answer, because this here is square root of 3. Of course, if you cannot reason it, you can always calculate it. This is 60 here, say this is omega 0, and this is 1. So then you can get it, you can get omega 0 as arc costangens of omega 0 divided by 1, this one, omega 0 divided by 1, should be 60 degrees. You put this in the calculator and it should return that omega 0 is square root of 3, which is the good answer. For frequency square root of 3 radians per second, an RC stage will give phase rotation of minus 60 degrees, which will be enough for this phase shift oscillator to complete a total phase shift of 3 times 120 degrees per stage. This is 360 degrees, and the Barkhausen criteria for oscillation will be satisfied and the circuit will oscillate. Thank you very much.